All right, so let's continue our discussion. So just a recap what we did before the break. So we look at how the wave move in a certain time. Essentially, that's what we did. And when the cycle of the oscillation on any point on the string completes one oscillation, so that's one period of time, the wave move to the right by exactly one wavelength, so one lambda here. Right? And using a very simple speed equal to distance over time, so you get lambda over period. So you can rewrite 1 over the period to be the frequency. Okay, so you have this formula which is v equal to f lambda. All right, so let's talk a little bit about these three parameters, which is actually very important in understanding how they change in different situations. So let's see, we have v equal to f lambda. So let's go through each one at a time. So f is the frequency. Of the wave. Who decides this? Well, the source of the wave decides this. So f is fixed, means it does not change. It's fixed by the source. Okay, so what is the source? Well, the one that originates the wave in the first place. So in the simulation in the web that I showed earlier, is the checking of the spanner that is the source. Okay, so the frequency is determined by this. Once this is set, meaning that once the wave has been propagated through the medium, no matter how much medium changes the wave encounter along the way, the frequency is always going to be the same. Okay, that's very important. Okay, just to emphasize again that frequency is fixed by the source. Nothing else can change it. Once the wave is produced, the frequency is not going to change. What about v? V is the velocity of the wave, or the wave speed. Wave speed or velocity. This is determined by the property of the medium. Or the wave can go through multiple mediums, right? And plural of medium we call media. So media is just many different type of medium along the way. So for example, you can have sound wave that is originating from a speaker, right? So maybe you just write it down. So I have a speaker that giving out sound wave, right? Like this. So speaker is set to giving out wave frequency of, let's say, 500 hertz. And let's assume that first section of this kind of situation is just air. So sound wave travel in air. And let's say after a few meters, it's going through a water tank here. So now it's no longer air, but it's going through water. And let's say afterward it's going through, a block of concrete. And this is water here. Okay, so the wave is 500 hertz. That's the frequency. Okay, the velocity of sound wave in air, well, roughly speaking, v is gonna be about 300 meter per second. okay, very roughly speaking. All right. But then when sound wave enter water, the medium changes. Okay, instead of air, you have now water. And what is the speed of sound in water? Well, I don't remember. It's probably 1,000 or something. So let's assume that that's the case. So V about 1,000. What about the frequency? The frequency, remember, does not change. So here, the wave is still having frequency of 500 hertz. But the velocity changes. Okay, well, that's fine. We're going to come back to that later. And then later on, sound wave enters concrete. The velocity will be even faster, let's say 2000. Again, this is kind of made up number because I don't remember exactly the velocity for sound wave in concrete. But in any case, even here, the sound wave frequency is still 500 hertz. So that's what I mean by the frequency is fixed by the source because the source is giving out at 500 hertz, right? No matter how many, you know, different types of medium that the sound wave is traveling through, it's gonna be always 500 hertz for the frequency, even though the wave velocity changes depending on the medium. Okay, so then how can we have this equation to be valid if one variable change, the other one does not change? Well, the third variable is the one to compensate for that. So lambda is the wavelength. Which is also changes according to lambda equal to V over F. So remember, F is fixed, but V changes. So lambda has to adjust such that this equation is true. All right. So what does it mean? It means that at these three sections, which have three different kind of medium, the wavelength is also different for every section. Okay, so let's just demonstrate this calculation really quickly. The frequency is all the same. Again, that's easy, right? So what's the wavelength here? The wavelength here is V over F. So it's gonna be 300 meter per second divided by 500 hertz. And of course, you're gonna have about 0.6 meter for the wavelength of sound in air. Okay. Now in water, V over F will change because V is now 1000. F is still 500. So lambda now becomes about 2 meters. Okay, so lambda changes. Lambda becomes longer in water. And then lastly, in concrete, V equal to F lambda again give you lambda equal to V over F. So V is 2000 meter per second. F is still the same, 500 hertz. So lambda now becomes 4 meters. So this is a very typical kind of way of figuring out what's happening in different kind of medium. Right? Frequency again, always the same. Velocity changes depending on the medium, so that means the wavelength also changes. Okay, so at every point in at every section, V equal to F lambda, that has to be true. Okay, so F is fixed, then the other two has to adjust themselves to make the equation valid. All right, so I hope this is clear enough. For the remaining time, we're gonna do quite a lot of, like derivation in terms of mathematical calculation. So the details might not be that important, right? But the important thing is at the end. So this is just to tell you that if you get lost in the derivation, don't worry too much, because if you understand what's happening at the end, that's probably good enough. Okay, so what we're going to do here is we're going to describe sinusoidal wave. So how exactly do we describe, how exactly do we describe sinusoidal wave? Well, we know at least that it has to be sine or cosine. But again, just like last time, we know that it has to be sine of omega t, right? We cannot just write some arbitrary random things in the argument of sine. Okay, so that, can I just paste it again? Okay, I can do that. So again, this is the sinusoidal wave that we drew earlier. And this is at t equal to 0, for example. So y and then x here. All right. So the first thing is we're going to try to describe this, which is, again, only valid at t equal to 0. But if we get the functional form correctly, for other time it's easy because you just replace x by x minus vt, right? We know that already. So the hardest part is probably this first step here. So the first thing we're going to write down is the amplitude of the wave. And obviously that's just how far away each section on the string is from the center line, right? So that's going to be the amplitude of the wave. So that's the maximum displacement each section on the string going to be from the center line, which is the case where there's no wave. Okay, so that's fine. So that means we can write y. I'm going to write on the right hand side, or maybe I can write it here. So y equal to a, which is the amplitude of the wave. And it has to be sine of some sort, sine of something, times x, obviously, because horizontal axis is x. So maybe I put it in red here. Right, again, the task here is to figure out what goes in front of x. And we're going to do kind of the same argument like what we had used before, which is we just see how much you need to increase x, which is the horizontal axis here, to complete one cycle of the oscillation. Okay, so that's going to be this particular point in the x-axis, right? And what is that? Well, that's, again, is the distance from the same spot. So that's going to be one wavelength. So this tick here is one wavelength. Another tick here is two wavelength. This is three wavelength, right? So wavelength is the distance where you go to the right and everything looks the same, right? But somehow we have to convert this into the angle in radian for sine, okay? And since this is the second time you have seen this already, I'm not going to spend too much time justifying this. So I'm going to write down right away what it should be, and I will ask of you to maybe convince yourself that this is the case. So the thing that goes in front is just 2 pi divided by lambda here. Okay, and quickly, it's just that when x is a multiple of lambda, right? So that means sine is 2 pi or 4 pi, right? So increasing x by 1 lambda is equivalent to increasing the whole argument of sine, which has to always be radian, okay, by 2 pi. So that's why you need to kind of normalize x by the lambda and then multiply by 2 pi here. Okay, so hopefully this is not too difficult to understand. It's very similar to the argument that we used last time to say that the thing in front is 2 pi divided by the period or something like that. Okay, but in this case, the horizontal axis is not time, it's the location on the string, right? So it has to be something which has the unit of distance. In our case, is lambda here. And this is true for t equal to 0, right? At any other time, well, if we go back to our picture here, right, the whole wave moves to the right, right? So this is exactly what the situation we saw earlier, right? The graph looks the same, but it's just shifted to the right. So that means what I can do is I can just replace x by x minus vt in the case of graph moving to the right. Okay, so this is nothing new. It's the same thing that we used in the first page of this lecture. So y now depends on two variables, x and t, right? So again, the first line here is at t equal to 0. So this is at t equal to 0. And the second line is for any time. So for any time, we're going to put in x minus vt in place of x. So this red x becomes x minus vt. Okay? Just replacing, direct replacement of x. Because we are shifting the whole wave to the right. And actually, that's it. That's all we need to describe the sinusoidal wave. Because we have v as a function of two free variables, x and t. And then both x and t appears here. And not only that, it appears as x minus vt. So it's a wave. So that we know. Okay. Well, the remaining thing is just introducing a few more terminology because, sometimes it's more convenient to use one variable, sometimes it's more convenient to use different variables. So I'm gonna go through all of them now, but I'm gonna go to the next page here. So y is the displacement of the string, and it depends on two variables, x, which is the location of the string, and t is time. And it's equal to the amplitude times sine of 2 pi over the lambda, and then x minus vt, right? I'm just copying what we had in the earlier page. So I'm going to multiply out the argument in the sine function. So I have 2 pi x divided by lambda, and then I have minus 2 pi v vt divided by lambda here. Okay, nothing crazy going on, just multiplying out the terms. So when we write this in, like a book or a paper or something, we don't really like to write, like a fraction, like like how do you call it, the numerator and the denominator. So sometimes people gonna call this 2 pi over lambda to be the new variable, which we call k. Okay, so it should be 3 lines here as the definition, but 2 is probably good enough. So 2 pi over lambda is k. This is called the wave number. Okay, and it's actually used quite frequently, so it's good to know. All right, and that's one thing. The other thing is that we have here v over lambda. Okay, remember if you have v and lambda, you can use this v equal to f lambda. So that means v over lambda is just the frequency. Okay. So in the next line, I can use the definition we just did, which is k, the wave number, x, minus 2 pi f, right, where f come from? F come from v over lambda, times time. So this is another way of writing the same thing. It's a little bit cleaner, I think, because you don't have fractions. But we don't have to stop here, because if you remember, for simple harmonic motion, 2 pi f can be written in terms of the angular frequency. So 2 pi f equal to omega, which is the angular frequency. So again, all of this does not introduce any new physics. It's just new terminology to make writing easier and more compact. Okay, so in the end, this is the form actually most people will be using because it's the most compact. There's no 2 pi anywhere, and it's very clean. Okay, but you have to know that every line here, they mean the same thing. Okay, so in your homework, you're gonna see a few problems asking you to identify what is k, what is omega, and from that you should be able to identify what is the wavelength, what is the frequency, and then from that you can calculate the velocity of the wave. Okay, so it's just asking you like whether you know how to read the wave function here, y equal to y of x and t equal to a sine kx minus omega t. Okay, and this is quite something that people use a lot in describing wave. Okay, so now that we have this, again, what is this? This describes the displacement of the section on the string, right? So if we have the displacement, what we can do is we can describe the velocity of the wave, exactly similar to what we had in the last lecture. But now the only difference is that our displacement depends not only on time but also depends on the location on the string, right? So what we're gonna do here is we're gonna fix x, which is the location on the string, and then find the velocity of that particular section on the string. So what I'm talking about now is that, again, this function describes a sinusoidal wave, right, which is the oscillation of, all the section on the string. And then I'm interested in just a tiny, tiny section on the string. And of course, this one is oscillating up and down, right? So I can, of course, calculate the velocity of this particular section without having to worry about any other point. So I don't care if the point here is also oscillating. No, I don't care. So I fix x, meaning that I just look at this particular section, and I just want to find the velocity, right? So to find the velocity, you need to do the time derivative, right? Just like v equal to dx by dt, right? But in this case, the velocity is in the y direction. You fix x. So what you do is this: v in the y direction at x, which is fixed, and then time. Now, because we have two independent variables, x and t, instead of writing the usual derivative, we have to do what is called the partial derivative. But it's actually nothing scary about it. It's just the regular derivative, except you treat everything except time to be a constant. So even though x appear here, then x is also fixed. Right? So this is the partial derivative. Again, it's nothing too fancy, it's just the usual derivative, but you just take everything except t to be fixed. Right? So in other words, to find this, you have to write down, and again, if you are not too familiar with partial derivation, differentiation is fine. You just need to see what we get in the end. Okay, so we have this. So I'm gonna replace this with our function, which is a sine kx minus omega t. Okay, and the variable that I'm differentiating is time. So that's the only free variable I have to worry about. Okay, so this is nothing too difficult, hopefully. And so I'm going to just write down what the answer is. So you're gonna get cosine, because differentiating sine, you get cosine. And you get a minus sign, minus omega here because of the chain rule. Okay, so it's minus a omega cosine, and the whole thing is the same, kx minus omega t. Okay, again, don't worry about x because we are keeping x fixed. So it's just like a regular differentiation with respect to time. Of course, next we can do is to calculate the acceleration. So again, acceleration in the y direction now depends on x and t, but again, we keep x to be fixed. So x is fixed again. So you just redo the differentiation again, like this. Okay, everything is the same. So I'm gonna skip a few lines and then write down the answer, which is minus omega square a sine kx minus omega t. And this should be very familiar to you because we saw something similar from last lecture. This here is just the y displacement, right? So this is just y of x and t. So what we have in the end is the acceleration of any point on the string is minus omega the displacement of any point on the string. And remember what this suggests? This suggests that the motion is simple harmonic. So that means every point, any point on the string, any point move as simple harmonic motion, which is what we studied in the last lecture. Okay, so this should hopefully kind of give you a closure of the whole story, which is that wave is just a collection of simple harmonic motion, or in this case, sinusoidal wave, right? So any point on the string behave like a simple harmonic motion, but wave is just a lot of them connected together. Okay, a lot of them connected together. So you can see that this thing, which is a very important that we saw last time, appear again here. Okay, so this should give you the close connection between simple harmonic motion and wave, sinusoidal wave that we are talking about here. Okay, so unfortunately we're not gonna have enough time to do the wave equation, but I'm gonna maybe do a brief outline of what we're gonna talk about next time. So remember that I said earlier that any wave, well, not any wave, any function that has the form of x plus minus vt is a wave. So we will try to restate this statement in a little bit different way. So next time we're gonna derive what we call the wave equation. Well, not really derive, we are trying to show that our sinusoidal wave satisfy this, what we call the wave equation. And the wave equation is a partial differential equation. It sounds quite scary, but the good thing is that we don't need to solve for that in this class. We just need to see what it is, and then hopefully maybe you can get a chance to use it in your later classes. But anyway, the wave equation looks like this. So you have partial derivative, which is second order, of any function which depends on both x and time. Okay, and this is going to be equal to 1 over the velocity square. The velocity here is the wave velocity. Okay, wave velocity of the wave speed, or the wave speed. Okay, v, and times the partial derivative now with respect to time. Okay, so you have this x, but now you have this time here of y of x and t. So if your function satisfies this equation, then that's a wave. Okay, so essentially I'm saying nothing new because I'm just saying like it here, because this is a very general solution of this equation. Okay, so it's kind of like if you have function which is in the form of x plus minus vt, then it's a wave. Or if you have function and you want to do a little bit fancier stuff, then you throw into this equation, which is the wave equation, and see if it satisfies this equation or not. If it does, then it's a wave. Okay, and next time we're going to show that y equal to a sine kx minus omega t, which is what we derived earlier for sinusoidal wave. This actually will satisfy the wave equation up here. Okay, it's actually not that difficult to show because it's just differentiation, a very rudimentary differentiation. You can try it for yourself, right? You can see that if you put this in here, then the equation is satisfied, right? So we are sure that what we have here is indeed a solution of a wave equation. So it's a valid wave. Okay, so everything is fine here. All right, so I think I might stop here for today. Maybe for a few minutes. Do you want to see this? Maybe I zoom out a little bit. Is this the page or the other page? Okay, so any other question, you can just feel free to just shoot me a message. If not, then I will see you on next Monday. And for today's video, I realized that at the very beginning, I record the sound, but I didn't record the video when I show the slide and simulation. Okay, so it might be a little bit strange, but you're gonna see the full thing from the moment that I start writing. Okay, but don't freak out if the video is a little bit strange for today. All right, then. Well, if there's nothing else, then take care, everyone, and I'll see you on Monday. All right? So have a good weekend, and don't forget to do homework. Take care, everyone.